We talked in the previous video about how to determine the strength of the magnetic force on a charged particle that is moving in a magnetic field. Now we're going to learn about how to determine the direction of the magnetic force on that charged particle. So what I'm going to say is, number one, follow the rules that are written here. When you are learning the right-hand rule, it is going to be awkward at first. That is completely normal. To help you practice the right-hand rule, I posted a worksheet on Canvas that has some practice right-hand rule problems. So just take a look at them, work through them, practice it, and at some point, the right-hand rule is just going to click in your brain, and this chapter is going to get a lot easier once that occurs. So anytime you learn a new skill, it is awkward at first. Don't let that stress you. That's completely normal. Also, you do not need to be a Cirque du Soleil master to perform the right-hand rule. Sometimes people will be curling themselves more than 360 degrees. All the motions you make with your arms and hands should come very natural. So the magnetic force is always going to be perpendicular both to the direction of motion and to the direction of the magnetic field. Again, direction of motion is always going to be in the same direction as a particle's velocity. So hold your right hand flat and aligned with your right forearm. Now make sure you're using your right hand and not your left hand. So your forearm should be perfectly aligned with your right hand. Align your forearm plus your right hand so that your forearm is pointing in the same direction as the direction of motion, the direction of velocity. Now notice that however your right forearm is aligned, your forefingers on your right hand bend easier in one direction than the other. So the forefingers, you don't want them to bend backwards. You want them to bend in the natural manner in which they would. So keep your forearm pointed in the same direction as the particle's velocity. Bend your forefingers until they point in the same direction as the magnetic field. Now, you have to keep your forearm pointed in the same direction as the velocity, but you are allowed to rotate your forearm. As long as your forearm is pointed in the same direction as the velocity, it's okay to pivot your forearm. Make sure that pivot your forearm, so twist your forearm until your forefingers can easily bend and point towards the direction of the magnetic field. So once you bend your forefingers to point in the same direction as the magnetic field, while your forearm is aligned with the direction of velocity, raise your thumb. The direction of your thumb will be the direction of the magnetic force if the charged particle is a positive charge like a proton. The direction of the magnetic force will be opposite the direction your thumb if you're talking about the magnetic force on a negative charge like an electron. So in this example, we have a magnetic field pointing in directly to the right. We have a positive charge. I see a positive charge, so I know that the magnetic force will be the same direction as my thumb when I eventually lift it. And the particle is moving down and to the right. So in the next part of this video, we're going to practice the two versions of the right-hand rule. The first version of the right-hand rule we talked about was to determine the direction of a magnetic field that is created by a long straight wire. The second version of the right-hand rule is to determine the direction of a magnetic force. Now, even though these are both called the right-hand rule, they are two different techniques and they do both apply in different scenarios. If we're considering the right-hand rule as the force on a particle, we consider the right-hand rule that I'm talking about on this slide. If we are using the right-hand rule to relate the direction of an electric current to the direction of a magnetic field, we use the right-hand rule with the thumb and the fingers, the straight part, the curly part, as described earlier. The version of the right-hand rule I'm going to talk about here is using the right-hand rule to relate the direction of current in an infinitely long wire to the direction of the magnetic field created by that current. Now, when I talk about the direction of the magnetic field or the direction of the current, knowing the direction of one immediately sets the direction of the other. So you only need to know one or the other. As I said previously, there are two versions of the right-hand rule. This version of the right-hand rule that I am discussing relates the direction of current flowing through a wire to the direction of the magnetic field that wraps around the wire. The other version of the right-hand rule that I will discuss in a few minutes is talking about when we want to find something involving the magnetic force. So how do we relate the direction of magnetic field wrapping around a wire to the direction of current in the wire? What we do is, if you think about an infinitely long wire, there are only two ways you could wrap around the wire. You could either wrap around the wire clockwise or counterclockwise. Now, clockwise and counterclockwise, those are a valid concept for talking about the direction, but clockwise versus counterclockwise isn't really the same as up, down, left, right, into or out of the page. Clockwise or counterclockwise could mean left or right, depending on if you are above or below the wire, as shown right here in the figure. So let's consider, as a first example, a wire that is coming out of the screen. So I take my right hand, I raise my thumb, and I align my thumb with the direction of the current. So if I align my thumb with the direction of the current, I notice that my four fingers will tend to flow in a counterclockwise direction. So that tells me that the magnetic field will also be counterclockwise wrapped around the wire from your guys' perspective. So from your perspective, if you are looking above the wire, the magnetic field is pointing in that direction, and if you are below the wire, the magnetic field will be pointing towards me. Another example of using this right-hand rule. If we have a magnetic field that points into the page if you're above the wire and out of the page if you're below the wire, that would be a scenario like what we have here. So if I wrap my four fingers into the page above and out of the page below, my thumb is now pointing to the left. So I could infer that a current flowing to the left will have a magnetic field that points into the screen above the current and out of the screen below the current. Now, notice that if a magnetic field wraps around a wire, no matter where you are, the magnetic field is always perpendicular to the direction of the current. So if the current is flowing to the left, then the magnetic field could be flowing up or down, into or out of the screen. The magnetic field will never be pointing in the left-right direction for this scenario here. In this scenario, if the current is coming into or out of the board, then the magnetic field could be flowing up or down, left or right, something in the diagonal. But the direction of the magnetic field here is always perpendicular to the direction out of the screen. In this part of the video, we're going to talk about using the right-hand rule to find the direction of the magnetic force. So this technique that we talk about will apply if we talk about a single charged particle moving in a background magnetic field, or if we talk about a wire in a magnetic field that carries a current. In both of those cases, we are talking about force. So this is the technique we want to use whenever we have a problem involving the direction of a magnetic force. So the first thing I'm going to do is I'm going to hold my forearm and four fingers on my right arm aligned with each other. And I'm going to align my forearm plus four fingers so that they align up with the direction of motion, with the direction of velocity. So in the picture behind me, the velocity is pointing down and to the right. So I want my forearm plus four fingers to point down and to the right as well. The next thing I'm going to do is I want to curl my four fingers in the direction of the magnetic field. When you do the right-hand rule, we assume that our fingers could only curl in one direction. So pretend you can't really bend your fingers backwards at all. I notice that if I curl my fingers down, my fingers are actually going to be pointing away from the magnetic field, not towards. But what I am allowed to do is I am allowed to rotate my wrist. As long as my forearm is still pointing in the same direction as the direction of motion, then I'm okay. So I can rotate my forearm, and now when I do that, I could raise my four fingers, and my forefingers could nicely point in the same direction as the magnetic field. So I have my forearm pointing in the same direction as the velocity. I have my forefingers pointing in the same direction as the magnetic field. If I raise my thumb will be in the direction of the magnetic force if I'm talking about a positive charge. My thumb will be in opposite direction of the magnetic force if I'm talking about a negative charge. So in this case, we have a positive charge, so the direction of the force on the particle behind me is out of the computer screen. The technique I described here, as I said, applies whenever we are talking about the direction of a magnetic force. So if we're trying to relate the direction of magnetic field to direction of a current, then we have to use the previous version of the right-hand rule. If we are talking about a current that carried in a wire and was the direction of the force on the wire, the techniques I describe here are the exact same, with the one difference being instead of aligning my forearm with the direction of V, I now align my forearm with the direction that the current flows in. But everything else I said still applies. I still might need to pivot my forearm, but once I have my forearm aligned with the direction of motion, the forearm is always aligned with the direction of motion. Then I curl my four fingers, I might need to pivot, and I raise my thumb to find the direction of the magnetic force.
Using what we just discussed about the right-hand rule, I'm going to ask the question, which way is the force on each of these charged particles? So as you need, pause the video, figure it out using the right-hand rule, and then we could compare answers. Now, in this diagram, the x-axis is pointing to the left or to the right across your screen. Positive x-axis is to the right, negative x-axis is to the left. The positive y-axis points towards the top of the screen, and the negative y-axis points towards the bottom of the screen. The positive z-axis is supposed to be taken to be pointing out of the screen. The negative z-axis is supposed to be pointing into the screen. Now, because these diagrams are 2D pictures on a screen, the author who drew these pictures did draw the z-axis with some perspective. But we will take the z-axis as pointing directly out of the screen towards you. So pause the video and see which direction the force on the particle in scenario A is. So if I align my forearm with the direction of the velocity, so my forearm is pointing to the left, I curl my four fingers so they are pointing towards the bottom of the screen, I raise my thumb, and my thumb is pointing out of the screen. So the force on this charged particle is going to be out of the screen or along the positive z-axis. Again, the positive z-axis is assumed to be pointing out of the screen. The author, again, just drew this z-axis with some perspective. So what direction will the force on the charged particle in scenario B be pointing? So if I align my forearm downward towards the bottom of the screen and curl my four fingers into the screen, I see my thumb is pointing in the positive x direction. So the direction of the force on this charged particle is in the negative x direction. It's true my thumb is pointing towards positive x direction, but here we're dealing with a negative charge. So the direction of the force is going to be in the negative x direction. For the third particle, the force on this charged particle is going to be 0. Whenever the angle between the direction of motion, direction of velocity, and direction of magnetic field is 0 or 180 degrees, the force on that charged particle is going to be 0. So in this case, we have 180 degrees between V and B, so the magnetic force on this charged particle is 0.